All right, I'm going to describe today's lab and do a little demonstration for you. We're going to learn how to titrate a mixture to determine the concentration of something in that mixture. In this case, we're going to determine the concentration of acetic acid in vinegar. So I'm going to change my share here so that you can see what I'm about to write. So let me make a little adjustment here. Okay, so vinegar has acetic acid in it. The acetic acid is dissolved and it is a weak acid. So this is acetic acid. When it reacts with water, it makes H plus ions that are aqueous and acetate ions that are aqueous. So when you look at a container of vinegar, so here's my bottle of vinegar. Inside of the container, you actually have acetic acid molecules, acetate ions, and H plus ions. Now the H plus ions are really H3O plus or the hydronium ion, but it's just simpler to write them as H plus. Now we could figure out the concentration of H plus ions, but that doesn't tell us the amount of acetic acid in the vinegar. To determine the concentration of H plus ions, you just get the pH, and then you take that pH and get the H plus concentration. So the H plus concentration is equal to 10 to the negative pH. And that's great, except the H plus concentration is not equal to the amount of acetic acid in the container. That's unlike HCl. So HCl is a gas. When you pass it into water, you get H plus ions and you get chloride ions. So if you put 10 molecules of HCl in water and start off with 0 here and 0 here, after time, so we'll call this time 1 and this is time 2, you'll have 0 HCl molecules and you'll have 10 of these and 10 of these. And in fact, if you put 1,000, or let's not say 1,000, let's say 10 to the 6, that's a million, and you start off with 0 here and 0 here, after time, you will get 0 here and 10 to the 6 and 10 to the 6. The important thing here is to see that this concentration and this concentration are the same. So the concentration of the acid is equal to the concentration of the hydronium ion. So this, if you measure the pH, gives you the hydronium ion concentration. And this also gives you the acid concentration. So that works well for strong acids, but does not work well for weak acids. So how do you determine the concentration of a weak acid? Well, you do a titration. So what is a titration? It's a method for determining the concentration or amount of a substance in a mixture. And for these titrations, you want a well-characterized reaction, so a well-known reaction. You want to quantitatively react all of the substance of interest. And based on your well-known reaction, you want to react it to a stoichiometric equivalence of reactants. And this stoichiometric equivalence of reactants is called the equivalence point. It's also called the end point. Okay, and so what do I mean by stoichiometric equivalence? Well, if we were reacting hydrochloric acid and say magnesium hydroxide, the reaction requires 2 moles of hydrochloric acid to 1 mole of magnesium hydroxide. So the stoichiometric equivalence would be 2 to 1. Now, of course, you may not have 2 moles of hydrochloric acid. Maybe you have 0.02 moles of hydrochloric acid, which means you would want 0.01 moles of magnesium hydroxide for a stoichiometric equivalence. So that's what I mean by stoichiometric equivalence. Now, of course, if the coefficients are 1 to 1, then the stoichiometric equivalence is 1 to 1 or equal amounts of each. One thing I did not write here that I do want to write is we need to have a way to recognize when we have reached the endpoint. For acid-base reactions, this is usually a color change. Sometimes it's a precipitation or something dissolves. So there's a number of different ways to recognize the endpoint. Okay, so normally, how do we do this reaction? What we do is we take acetic acid, which is found in vinegar, and we react it with a strong base like sodium hydroxide. Now we make a solution of this strong base, and the reaction is quantitative. And that's liquid, and that's aqueous. And you can see the ratios are 1 to 1 gives you 1 to 1. So the stoichiometric equivalence is for every one of the acetic acid molecules, you want 1 sodium hydroxide. That's your stoichiometric equivalence. Now, this is a strong base, and as such, it's dangerous. It's used as drain cleaner. In fact, it's used to dissolve people. Like if you're in the mafia and you want to get rid of a body, you stick it in one of those 55-gallon drums, you add in a bunch of sodium hydroxide, and the body dissolves. Okay, so you have some of this in your kit, but I've decided that we're not going to use it because of the danger. So do not use it, keep it sealed. And if you want, you can pour it down your drain with some water, running water, and it works as drain cleaner. Okay, so what I would suggest you just keep it sealed and return it with your kit when you're done. So this is normally what we do. Now, to do this reaction, we need to know the concentration of the sodium hydroxide. So normally, we actually titrate the sodium hydroxide with something called potassium hydrogen phthalate. This is potassium hydrogen phthalate. Now, you can see I've only drawn one hydrogen. That's the hydrogen in the name. That is potassium, so that's the potassium in the name. And the rest of it is phthalate, or the phthalate ion. This reacts with sodium hydroxide. And here's what happens to the potassium hydrogen phthalate. Now, the potassium hydrogen phthalate, because it's an acid, it is a proton donor, and that's the proton it donates. So you get that. And that proton adds to the hydroxide ion to give you water. And so normally we write the sodium here. So this would be called sodium potassium phthalate. No hydrogen now. And we're going to call it potassium sodium phthalate, keeping in alphabetical order for the two ions. Okay, so this is normally what we do. And the reason we use potassium hydrogen phthalate is because it's an acid and it's a solid at room temp and it's very stable. It does not absorb water from the air. It doesn't decompose. This stuff lasts forever. So it's a very stable acid. It's a weak acid. It poses no harm whatsoever. Okay, so these are normally the reactions that we do. And we do this reaction usually first to determine the concentration of the sodium hydroxide solution. Then we do this to determine the concentration of the acetic acid solution. However, we're not going to be doing that. Now, I do want to teach you one more thing about the potassium hydrogen phthalate. The deal is that wherever you see lines, those are bonds. And the bonds connect together atoms. If we do not see the atoms where the bonds meet, they are carbon atoms. We normally think of two lines parallel as a double bond, a single line as a single bond. So what I'm doing here is I'm filling in all of the carbons. Now, oxygen bonds to hydrogen through a single bond, so I'm going to draw that like that. And here we know the potassium is an ion, and I'm going to put a little plus sign there. And since we know that this guy here has to be a charge so that K plus and this charged particle equals a zero charge, there's a negative. And we're going to put the negative on that oxygen, and that's why these guys hang together. Now, in addition, for every carbon that we have, we want to make sure it has 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yes, we can count bonds twice. We just count how many bonds there are to a particular carbon. We don't care if it's bonded to another carbon. We just count all of the bonds. Now, if you look at this carbon on the bottom, you'll see 1, 2, 3 bonds. So it doesn't have 4 bonds. How do we get 4 bonds? And the answer is you add a bond to hydrogen. So we're going to do that for these 4 carbons here on the ends. And you can see that when you count up the formula, the carbons, you get 8 carbons. Hydrogens, you get 4 or 5. And for oxygens, you get 4. And then you get there, and that is the formula for potassium hydrogen phthalate. And again, because it is an ionic compound, a metal and nonmetals, you want to put the cation first, so potassium. Over here, we would put the potassium, sodium, and then it would be C8H4O4, potassium sodium phthalate. Okay. So we're not working with sodium hydroxide. What are we going to do? Well, what we're going to do is we're going to take that potassium hydrogen phthalate and we're going to react it with sodium bicarbonate. So this is one of those gas forming reactions. And part of your job is to figure out what the balanced reaction looks like. Remember, this is a bicarbonate, and when it reacts with an acid, you get 3 things. I'll let you figure that out. Okay, the important thing here, though, is I will tell you that the ratio of these are 1 potassium hydrogen phthalate to 1 sodium bicarbonate. Now, I should tell you that potassium hydrogen phthalate is often abbreviated as K for potassium, H for hydrogen, and P for phthalate, which is unfortunate because that is not the formula. It's just an abbreviation for the name. Remember, the real formula is KC8 H5O4. That's the formula. So don't be fooled by this KHP and think, oh, there's one potassium, one hydrogen, and one phosphorus. Well, goodness, there's no phosphorus in there. So that's just an abbreviation for the name. Okay, so you need to figure out the balanced reaction here. And what we're going to do, our goal for this is to figure out, determine the molarity of sodium bicarbonate. And for molarity, molarity is the moles of sodium bicarbonate per 1 liter of solution. So, for instance, if we have a 1.5 molar sodium bicarbonate solution, that indicates 1.5 moles of sodium bicarbonate per 1 liter of solution. So you want to be able to take something that says 1.5 m and turn it into a fraction like this. And whatever you do, do not do this. So this is a big no-no. 1.5 m sodium bicarbonate over 1 liter of solution, because this is wrong. What this actually means is 1.5 moles of sodium bicarbonate over 1 liter of solution over 1 liter of solution. So that M includes a liter in it. And so we want to make sure that we do not turn this into that without and put it over a liter, because you're forgetting something. So don't do this. This is a no-no. I'm going to put a big X through here. So when you turn this into a ratio, you put mole on top and liter on the bottom. Okay, so we're going to determine the molarity of our sodium bicarbonate solution. So I'm going to go ahead and get started with that and show you what you want to do. So you want to make a saturated solution of sodium bicarbonate. And what I'm doing here is I'm going to start with a beaker, and I'm going to start with one that says it's a 50 milliliter beaker, because I'm going to make about 25 mils of solution. So you want to use your balance, and I'm going to go ahead and tare my balance. And here I have some good old baking soda, which is sodium bicarbonate. Now, to make a saturated solution, you dissolve about 9 grams in 100 milliliters. So in 25 milliliters, that would be about 2.5 grams. So I want to make a saturated solution, which means I want to make sure that as much sodium bicarbonate will dissolve in my water as is possible. And so I'm going to put in 3 grams, because that should be more than enough. Okay, and I have 3.25 grams. If 3 grams is enough, 3.25 grams is certainly enough. So I'm going to pop that all into there. And let's see. I want to clean this out with something. I guess I'm just going to use my sleeve. I mean, it is just baking soda, right? Okay, so I'm going to turn my balance off. And I have my sodium bicarbonate. And now I'm going to add about 25 milliliters of tap water. So on the sides of my container, I can see 20 and I can see 30. I'm going to fill this up to between 20 and 30, and I should end up with a saturated solution. So the saturated solution means we have the maximum amount of sodium bicarbonate dissolved as is possible. And what that will mean for our solution is that some of it will remain undissolved. So I'm going to stir this, and you can see it's getting nice and cloudy. And I'm just using my spatula. And like to do this in a clear container so that you can see if there's still some sodium bicarbonate that is undissolved. Okay, and you can see, I can see actually from the top that it's starting to settle. And if I turn this to the side, you can kind of see that it's settling a little bit. Okay, so you want to let that settle all the way. I'm going to do this a little faster than I would normally do it because, you know, we're kind of in a crunch for time. So once it is settled and the top of the solution is clear and colorless, meaning the top of the solution doesn't look cloudy whatsoever, and this solution still looks cloudy. Once that does happen, though, what you want to do is decant the solution into another container. And so I happen to have another container somewhere. Here we go. Here's my larger beaker. And I want to make sure, I don't actually need this beaker to be dry, but I don't want it to be sopping wet. So I do want to dry it a little bit. So what I'm doing is I'm shaking the water out of it. And here's the beaker that I'm going to put my saturated solution in. Now, the saturated solution, again, means you have the maximum amount of sodium bicarbonate dissolved as is possible. And the stuff on the bottom is the stuff that is not dissolved. We don't want that. We're going to decant the solution into here. Decant means to pour the solution into another container, but to leave the solid behind. This is often what is done with wine, because a lot of times when wine is bottled, some residual stuff gets through with the wine and it settles on the bottom naturally. And so when you pour the wine, you don't want those particles to come out with the wine. You want the wine to be clear and you want it to be colored, usually, if it's a red wine, not colored if it's a white wine, but you don't want to see bits floating around. So you decant the wine, which means you don't want to take the wine and just chug it into your wine glass because you'll get those residual particles in there. Now, of course, it doesn't matter if you buy cheap wine, but the good wine often has particles in it. All right, so I'm going to decant. And I want to make sure that none of the solid goes into this container. And so when I'm done decanting here, you can actually see the solid piled up kind of at one side of the beaker, and I have a clear and colorless solution here. Okay, so this is my saturated sodium bicarbonate solution, and I am going to need I'm going to need a pipette for that. So I've got a pipette right here, and I'm going to label this pipette with a NaHCO3 on it. And I just have to make sure that I don't grab it over the label, otherwise the label will come off. And what I'm going to do with this is I'm going to rinse this pipette with the solution. So I've just rinsed the pipette, and there's my saturated sodium bicarbonate solution. So I'm going to put that off to the side. Now I'm going to bring my balance back out, and I'm going to use my Erlenmeyer flask. This is the conical flask. You can see it's wet on the inside, but that's okay. It doesn't need to be dry on the inside. I do like it to be dry on the outside. I'm going to put it on my balance and turn my balance on. So right here, I have my potassium hydrogen phthalate. And what I want to do is I want to take my spatula and make sure it's nice and dry and clean. And I want to put about 0.18 to 0.22 grams of potassium hydrogen phthalate in my flask. So here we go. Try not to get it on the sides if you can avoid it. Okay, and so you can see that I have 0.22 0.21 grams of my potassium hydrogen phthalate. Now, if you get more than 0.22, just work with it. Okay, so I want to record that information, the 0.21 grams, of course, because that will be important for later. Okay, so now I have my solution with, or not my solution, I have my potassium hydrogen phthalate in this container. And what I want to do is I want to use some indicator solution with that. So this indicator solution you can see is a rich purple color. Oops, and I have some leafing material in there. I didn't want that. Now I made this by putting a whole leaf in a pot of water, and I boiled it for about a minute or two. And I didn't put much water in there, maybe 100 milliliters, maybe 200 at most. And I got this rich colored solution. So what I want to do is I want to add indicator solution to my potassium hydrogen phthalate. I'm going to add 10 drops. So there's my 10 drops of solution. And you should be able to see that this is turning pink at the bottom. Now, what's a nicer way to see that this is turning pink? And the answer is, I will show you. Let's see, I need some paper. Here's a nice piece of paper. So you can really see that pink pop against the white background. Now in this container here, I put my rinse sodium bicarbonate, and let's see what happens when I add my indicator to that. Okay, so you can see that it's blue. This is the color we're looking for our endpoint. Okay, that bluish color. So what I'm going to do here now is I'm going to titrate this with my sodium bicarbonate solution until this turns blue and stays blue. Now, I'm going to tell you a few things before we get started. You will see little grains of potassium hydrogen phthalate in the bottom of this, because it turns out the potassium hydrogen phthalate, even though it has the potassium ion, it is not very water soluble. And the reason for that is because even though it's an ionic compound with potassium in it, the anion is huge. And so the potassium ion is unable to completely dissolve the molecule or the counter ion. But as the reaction ensues, you'll end up with one potassium, one sodium ion, and two charges on the phthalate ion, which is water soluble. So before we get starting with this, there is one more thing you want to do. And that is to determine how many drops are in 1 milliliter of your pipette. So I'm going to fill my pipette to 1 mil. And then I'm going to count drops. 1, 2, 3, 4, 5. And it takes more than 5. Now, I'm going to warn you about this. It does matter how you hold your pipette. If you hold it straight up and down, the drops will probably be different than if you hold it to the side. So which way should you hold it? And the answer is whichever way you wish. Just make sure that once you decide at what angle to hold your pipette, you keep holding it at that angle. So if we take a look at what we've done so far and write down the directions, let's see, where's all my paper? I'm going to write down some of the things that we've done so far. So these are just general big directions, not tiny little, here's exactly what you do directions, because that's in your written lab description. So we're going to make a saturated sodium bicarbonate solution. We're going to calibrate the pipette. And we're going to put between 0.18 and 0.22 grams of KHP in a flask with 10 drops of the cabbage indicator. And maybe I could put a little thing here about the cabbage indicator. Boil a leaf in water for 1 minute. And then strain. You want to have a really, really deep, dark colored solution. Okay, so that's what we've done so far. So now we titrate our sample until it turns this color. Now, one of the problems with this titration is that one of the products is carbon dioxide. Carbon dioxide in water is an acid, and it'll keep the solution pink. But as the carbon dioxide is released from the solution, it will not make the solution acidic anymore, and the solution will turn eventually this color blue. But it takes time. So that means when you titrate this, you want to titrate it slowly. Now, what I'm going to do is I'm going to take this off screen so you can't see what I'm doing. I'm going to add a whole bunch of drops. And I'm going to show you what's happening now. You can see that it is bubbling a little bit on the edges. And maybe I can zoom in on that a little. And we'll focus. So you can see the bubbling there. And I'm going to swirl this, and you can already see the color is changing from a nice pink to a purple. Now, what color do you get when you mix red and blue? You get purple. So this is starting to react. Now, we want this color to match this color. Now, I can tell you that you are not done titrating if you see little bits of solid in there, which I see. So what you have to do is just be patient, swirl, and keep going until all of the solid particles dissolve and until you get a blue color like we see to the right. So here, if you have no patience, you should just pack it in and go home because it's over. You'll not be able to do this lab. You have to have patience. Now, if you want to, you can add a little bit of water to rinse down the sides, but don't add too much because you dilute the color and it's harder to tell the color. Okay, now you don't know how many drops I've added, and neither do I, to be honest. But from here on out, I probably want to drop the drops in 1 drop at a time. Now I'm just going to drop in a few. And remember, our goal is to get the same color as this blue over here. Now it takes a while. And another thing I want to show you is you might be able to see from my pipette, there are some air bubbles in there. And here I have a little bit of air bubble at the end. I don't want that. I want a full-on drop, no air bubbles. So you want to be careful about that. And so what I often like to do is when I put my pipette in my solution, I'll squeeze the bulb, let it draw up the solution, and that way I have no air bubbles in there. So when I squeeze the very first time, I get a drop. But when I let go, I get air in there. So you have to keep it squeezed or squoze, I don't know what the word is, and add drops in. Now, remember how pink this was to begin with. And if you wanted to, it would not be a bad idea to have some potassium hydrogen phthalate. So I just had a little bit left over, so I dumped it all in here. add 10 drops of indicator. So there's my indicator and my potassium hydrogen phthalate. And I'm just going to add a little bit of water to help it to mix. And so here we can see what I had to begin with, what I'm reaching for, and what I have here. So you can see that this is really a mix between these two. And also when I swirl this and I look at the sides, I can see little bits of solid still undissolved, which means that some of my potassium hydrogen phthalate has not reacted. So remember, we're going to add dropwise and swirl. And what you want to do is you want to be able to see a color change where it goes from this kind of purplish color to this blue color with the addition of 1 drop of sodium bicarbonate solution. Okay, now as I look at the sides, I can still see some potassium hydrogen phthalate that has not dissolved. I'm going to wash the sides down a little bit. And you'll notice I keep holding this at an angle. And the reason for that is that I put all the solution in one part of the Erlenmeyer flask, and it's easier to see the color. You can see that I am rapidly approaching this blue color here. And we're just going to be patient. And we're going to swirl and let that react. When it gets to be this bluish color, I know I'm really close. So I want to be careful not to add my sodium bicarbonate willy-nilly at this point. I want to be really patient at this time, swirl it, and give it time. Remember, you have to give it time because the carbon dioxide has to escape from the solution. The carbon dioxide is making this acidic, and when it escapes, it makes it less acidic, or more of this blue color over here. Okay, so I'm going to add maybe another drop, see what happens. You'll notice I'm swirling it, trying to rinse the sides down. And by doing that, I don't have to add more water to the solution. But you have to be careful because if you swirl some of the solution out of the neck, then you have to start over. Now you'll notice what I'm doing here is I'm swirling this pretty well. I'm agitating it. And the reason I'm agitating it is because it helps to remove the CO2 from the solution. So can you see how it looks like we've got a pretty good match here now? Okay, so that's what we're looking for. Now you want to do this titration 2 times. And you want to save the second titration, and you want to save it in a container. What I'm going to do is I'm going to rinse this container out. This is my saturated solution. And I'm going to rinse it out into another container I have here. Okay, so I want to keep this solution around, so I'm going to put it in there. Okay, I'm going to go ahead and add 1 more drop and see what happens here. And you can see here that with 1 more drop, the color hasn't really changed. And so, what number would I use? Would I use the number of drops that I just put in and include that extra drop? And the answer is no, I wouldn't include that extra drop because it really didn't change the color. So I want to keep that for comparison. And what I'm going to do is I'm going to take my flask and I'm going to rinse it out with water. And remember, you're going to do this titration 2 times. So what do we do next? Next, we use our vinegar. And let's see, where is my vinegar? Ah, here it is. So here's my jug of vinegar. You can see right in big letters, it says 5% acidity. And what I'm going to do with my vinegar is I'm going to take a pipette. If I can find one. Well, I have to go grab a pipette. So I'm going to pause this recording for a moment. Okay, and I'm back. Doesn't seem like I was gone long at all, does it? So here's my container, and I'm going to put some vinegar in there. I don't need much. White vinegar works best. And what you're going to do here is you're going to take 1 milliliter of your white vinegar, and you're going to put it in your flask. So here we have precisely 1 milliliter of white vinegar in our flask. You're going to add 10 drops of the indicator solution. And you can see that this turns the same color pink as the solution with potassium hydrogen phthalate, which is over here. And now what you're going to do is you're going to titrate this to an endpoint so that the color matches this or this. So I'm going to go ahead and add. Remember, you want to count the drops and you want to add the sodium bicarbonate solution slowly. You'll notice when I swirl this, I get bubbles, and that's the CO2 that's being formed as one of the products. And it's okay that it bubbles. We actually want the CO2 to bubble up out of solution. So I am swirling this, swirling this, swirling this. And you know, when you get to a nice purple color like this, you want to start adding the drops in one at a time. And I'm not going to do that, but I'm just going to add a whole bunch here. And you'll notice that the solution turns this blue color, almost a purplish blue. And I'm swirling, 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 shaking, shaking, shaking. And you can still see it's that kind of bluish color, but it's more blue now than it is purplish. And we are getting close to matching the color over here. And so I'm not adding any more sodium bicarbonate. I'm just shaking it and being patient. And probably in a few minutes, this color is going to match this color over here, which seems to match this color here. Okay, so if it doesn't turn the same color as this over here, I can always add more sodium bicarbonate solution, 1 drop at a time, and see if I can get a color match. Okay, so the important thing here is to count the drops. And they're getting pretty close. You can see these two match pretty well. Okay. Shake that up well, trying to get the CO2 to leave. And they are getting even closer match in color. So you want to get those to color match. All right. And count the number of drops it takes to turn this to that particular color. So I'm going to put these all up over here, out of the way. And we'll write down what we also have done. So you put between this, da, 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 and then titrate with the sodium bicarbonate to the endpoint. And remember, we can see the endpoint by adding 10 drops of indicator, and we'll say 3 or 4 drops of sodium bicarbonate solution. So that's the endpoint. That's the color of the endpoint. And then you want to, after you do that titration, is repeat. When you repeat, get a different mass of potassium hydrogen phthalate. Don't get the same mass as before. Okay. And then 5, you're going to titrate 1.0 milliliter of vinegar with the sodium bicarbonate solution. And of course, what you're going to do is you're going to add 1 ml of vinegar, 10 drops of indicator, and count the drops of sodium bicarbonate solution to reach the endpoint. Okay, so here are all of those solutions. You can really see that these two are color matched now. You know, it took a little bit of time, but they're color matched. And pretty close to this one here. Okay, so you can play with this and see, well, can I get this to color match precisely? And what would you do? Well, you just add more bicarbonate solution. So I'm just going to add a ton more and see if it does finally come out to be the precise same color as this. And what is one of my issues with comparing these two things? And the answer is really simple. One of them's in a clear and colorless container. The other one's in a white container. So that may have something to do with the color I see. Alrighty then. So as far as the calculations go, you're going to need to calculate the molarity of your sodium bicarbonate solution. So to do this, the molarity of your sodium bicarbonate is going to be equal to the moles of sodium bicarbonate over the liters of sodium bicarbonate solution. Okay, so what you're going to do, of course, to do this is you're going to take the number of drops of sodium bicarbonate, and you're going to turn that into milliliters of solution. And you're going to do this because you're going to have calibrated your pipette so you know the number of drops per milliliter, or the milliliters per 1 drop. Now, this is far more useful to know. So we'll call this D, milliliters per 1 drop, for D and D. Okay, so if you take the number of drops here, you can turn that into milliliters of sodium bicarbonate solution. Then you can take that, I'm going to write this down here. You can turn that into milliliters of solution, and then you can turn that into liters of solution, because to calculate the molarity, you need liters of solution. Okay, how do you get your moles of sodium bicarbonate? Well, you have your grams, K grams of potassium hydrogen phthalate. You use the molar mass of potassium hydrogen phthalate to calculate the moles of potassium hydrogen phthalate. And then you use your balance reaction to calculate the moles of sodium bicarbonate. So with these two numbers here, this L, that would be the, we'll call this Y. You calculate this X, you plug it into this formula, and you get the molarity of your sodium bicarbonate solution. Now, how do you calculate the molarity of acetic acid in vinegar? Well, you're going to do the same thing. To get the molarity of acetic acid, You're going to need the moles of acetic acid per 1 liter of solution, which is 1 liter of vinegar. Now, you know you're using precisely 1 milliliter of vinegar. Convert that into liters of vinegar. How do you get your moles of acetic acid? Well, you used your balanced reaction between acetic acid and sodium bicarbonate to work that one out. So I'm going to leave that part for you to figure out. And that's that. So what do you do with all of these materials when you're done with them? Well, what you're going to do is you're going to collect them all in one container, and you're going to pour all of this down the sink with running water. And of course, if you want to, you can play with it a little bit. So here, watch what happens when I add vinegar to this. You see those little splashes of pink in there? And you can almost make it look like a tie-dye. Okay. Isn't that neat? And it's bubbling. What are those bubbles? CO2. Oh, and now I've turned it pink. Now I want to turn it back to blue. I can add some sodium bicarbonate. And it's turning back to blue. There we go. So I could do this all day long, except I'm not going to. And that is your lab demonstration for the titration of vinegar to determine the acetic acid concentration. All right. Thank you much for listening.